Welcome back to Life on Mars. We're not quite on Mars yet, but we're going there. A lot of stuff happened this week, so the first thing I want to do is introduce you to these guys. Okay? Riley on the left, Comet on the right. Guess which one is mine? So I have an 8-week-old puppy because, you know, when you're old enough, you stop sleeping, so you might as well just have something else to keep you up all night. So we're very happy with Comet. This is Comet's older brother, sort of, Kepler. Okay? What's amazing about these dogs, these are soft-coated Wheaten Terriers. They're all born red and black like this, and then they all turn white. Kind of cool. So that's the most important thing that happened in my week. Okay? The important thing to know about that is the reason I have this Mountain Dew is because I'm really not sleeping very much. So if I fall asleep during class, you'll know why. All right? All right, this is the other news. I wanted to tell you something about this. It has nothing to do with Mars, but it has to do with astronomy. An announcement came out on my news feed this morning, could have been really early this morning, okay, about the 30-meter telescope, the TMT. The TMT is in various stages of construction and not construction. It's the 30-meter telescope, TMT. The announcement was that the Hawaiian Supreme Court has approved allowing the construction of this telescope. It's a $1.4 billion construction project. A lot of you seem to be astronomy fans, so let me both give you the positive and the negative of this. And here's another picture. This is where it would go. This would be the TMT on the summit of Mauna Kea. The summit of Mauna Kea, the actual summit is right about there. It's 13,996 feet, so if you actually go there, you'll find a little pile of rocks that people have built to get it to 14,000. Okay? And I've had the privilege of using most of the telescopes you see up there over my career. It's a really fun, exotic place to go to. There's not much air. But the important thing to know about the TMT is if and when it's built, it will be a revolutionary telescope, 30 meters across. That's bigger than the size of this room, the mirror. It's huge. The biggest telescope on the planet right now is the Keck, which is 10 meters across. So 3 times bigger this way, 3 times bigger that way, 9 times more collecting area. It's a big telescope. $1.4 billion is also a lot of money. Yes, sir. Yes. It's not one mirror. It's lots of little segments that work together, and then it will have all the widgets to make the atmosphere effectively disappear, so you don't get blurred images through the atmosphere. A big telescope can collect more light, so you can see things that are fainter, which means you can see things that are further away, which means astronomers using this telescope hope to be able to see objects that are basically at the edge of the visible universe, as far back in time and space as we can look. Fantastic. The problem with this, as I see it, is the price tag, $1.4 billion. The total budget for all of astronomy in the United States today from the National Science Foundation, which is where virtually all the money comes from, is about $200 million a year. This is being built sort of mostly with private funds, most of which have not actually been raised yet. They have maybe half of that, which is a lot of money. The money they have to build this will build it. It won't pay to operate it, and it won't pay for the instrumentation that will hang on it. And even one camera, a visible light camera on this thing, will cost $100 million. That's half of NSF's budget for an entire year. And they're going to be asking the NSF for that money. This telescope will both be revolutionary and has the potential to bankrupt U.S. astronomy. So it'll be very interesting to see how this plays out over the future. The reason the Hawaiian Supreme Court got involved is that the summit of Mauna Kea is considered a sacred site for Native Hawaiians, and they don't want more construction on the top of Mauna Kea. They want to preserve it as it is, and the Supreme Court has given the go-ahead after almost a decade of protests and court battles and whatnot. So it looks like it may get built, but I think it's not a done deal because the protests at this point are going to move out of the courts onto the construction paths. You're going to see news releases of people sitting on the road to block the trucks going up to the summit. That's the next phase of this. But keep your eye on it because that's news. All right. Back to Mars. Some of you may remember the famous face on Mars. Okay? The face on Mars was discovered in 1976 when the Viking orbiter was taking pictures of the surface and found this incredible face, which means someone lives there, right? Okay. So for Halloween, I thought I'd show you the face on Mars. This is an update of the face on Mars. This is a Mars Reconnaissance Orbiter image of the face on Mars from 2001. The face is about a mile across, 1.5 kilometers across. It's a mesa. And there's the eyeball, and there's the eyebrow. And, it's obviously not a face. All right, let's go back to Mars. Real Mars.
I'm sorry, could you go back that picture?
Shortcut.
Did you notice the hair looks like Trump?
Did all of you hear that? She said, "Did I notice the hair looks like Trump?" I just... These PowerPoints will be online somehow in the OSHA website soon. You can download the image and do whatever you want with it. All right. So now we'll go to the real Mars. We've been talking about Mars. Something that I wanted to clarify because there was a little bit of confusion with a couple of you after last week's class. 2 weeks ago, we talked about the water in the atmosphere of Mars. Last week, we talked about the water on the ground on Mars. So those are not in conflict, even though they're vastly different amounts of water. The evidence shows that ancient Mars has what we call a global equivalent layer of possibly as much as 3,000 feet of water. So if you took all the water which was once on Mars, you get an ocean covering the entire planet 3,000 feet deep. We don't know how much of that water is still there. There's some evidence that says as much as 85% of it has disappeared to space, which means if you could take all the water in the ice caps and in the subsurface reservoirs and put it on the surface, you'd get a layer a few hundred feet deep. 2 weeks ago, we talked about the atmosphere of Mars, that the total amount of water in the atmosphere of Mars is at most a few cubic kilometers. Spread that evenly around the planet, you get a global equivalent layer of a few microns, 25 or so microns. One of those is a measurement of how much water is in the atmosphere today. The other is a measurement of how much water is under the surface or in the ice caps today, not in the atmosphere as water vapor or clouds. So those are not inconsistent numbers. All right? Now we'll move on. A lot of words on some of these slides. These are mostly for me, so I know what I'm talking about, but you can read them as much as you want. One of the things I want to talk about today, what we're going to be talking about today is the set of observations that people made over a century trying to prove there was vegetation on Mars. One of the amusing things to me about this is that everyone has always called Mars the red planet, and in the 19th century everyone talked about Mars being red, and you'll see a little bit about that. The magazine, Cornhill magazine, which was published in London in the 1870s, beginning of the 1870s, spent a lot of time writing about astronomy. And in one of the articles, they wrote about how Mars is a charming planet, well fitted to be the abode of life. And they further wrote, the far greater lightness of the materials they would have to deal with in constructing roads, canals, and bridges, or the like. Let's stop right there. Mars's gravity is weaker than the Earth's gravity. If you were on the surface of Mars, you could jump twice as high because gravity is only half as strong. That means if you want to lift a railroad tie, you're twice as strong. Right? Because the railroad tie is not pulled down as heavily by gravity. That's what's meant here by the writer who actually understood something about Mars. This is good. The materials they would use to build roads, canals, and bridges would be lighter. They wouldn't be weaker, but they would be lighter. We may very reasonably conclude that the progress of such labors must be very much more rapid and their scale very much more important than in the case of our own Earth. So anybody living on Mars would have a big advantage. So they're way ahead of us. I introduced you to Camille Flammarion sometime in the last couple weeks, who was this great popularizer of astronomy in the late 19th century, their version of Carl Sagan at the time. And he wrote, since it is the surface which we see, not the planet's interior, the red color. So now I want to emphasize, the red color. People talked about the red color of Mars. The red color ought to be that of the Martian vegetation. So for some reason, Martian vegetation is red. Since it is this species of vegetation which is produced here, the continents of Mars, he concluded, seem to be covered with reddish vegetation. There must be something on the lands, whether it be moss or even less. Mars has a species of vegetation which do not change color with the seasons, in the same way that on Earth olive trees and orange trees are as green in winter as in summer. Most of our trees, our grass, our vegetation turns brown in the winter. Our vegetation changes color. Mars is always red. So clearly the vegetation isn't changing color, so it's got to be made of deciduous type of trees, right? Or evergreen types of trees. So olive trees and orange trees are green in winter because they don't lose their leaves. This characteristic color of Mars, the red color, is due to the color of the grass and other vegetation which must cover its plains. Can there be red meadows and red forests up there? This is great stuff. Now, let me remind you of chlorophyll, because this is where we're going. Because with this idea that there must be trees or grass or vegetation on Mars, people began searching for chlorophyll. And I showed you this plot of chlorophyll before. This says percent absorption versus color or wavelength of light. The chlorophyll molecule absorbs some of the light that's incident on it. The reason leaves are green is because sunlight, which has all the colors, hits the leaf, which has the chlorophyll in it, and the chlorophyll absorbs the blue and the purple. Percent absorption, nearly 100%. Almost all of the blue and purple that hits the leaf just stays in the leaf. Most of the red and orange stays in the leaf, but the green and yellow bounce off the leaf. That's what this plot tells us. This is the signature that astronomers were going to use to search for proof that chlorophyll exists in the plants on Mars. The logic here is, let's just say, flawed. Okay? Mars is red. Mars is not green. So why would you look for evidence of chlorophyll, which is green? But this is what they went and started to do. The guy who started this was a Russian, Gavril Tikhov, who worked at the Pulkovo Observatory, which is just outside of Moscow. His early career must have been terrible, because first you have the Russian revolutions in 1905 or so, and then you have World War I, and then you have the Russian Revolution #2, and he's busy trying to do astronomy at a telescope just outside of Moscow while Moscow's being run over. Astronomy wasn't the most popular thing to be doing at the time. But he started this. He decided he would use green filters, what he called looking for green patches on Mars, just by taking his telescope and putting a filter on the front of the telescope like you'd do on a camera, and looking for the color green. By 1909, he had concluded that Mars doesn't look green. The dark patches are dark, but they don't look green. Okay. Now, that might be consistent with the fact that Mars wasn't green. But he was determined to find out what color the vegetation on Mars was. Right? 20 years later, he had to relocate to Kazakhstan to a telescope, an observatory called the Alma-Ata Observatory, where he spent the rest of his career. He decided that his argument now would be that the absence of that green color was not proof that life didn't exist. It just proves that life on Mars is not green, and therefore that life grows without chlorophyll. And most of what he then did for the rest of his career wasn't astronomy, but was botany. He began searching for plants that didn't have much chlorophyll, or at least weren't green. And he started searching for plants that grew at very high altitude, where the oxygen was poor, or in very cold climates, which would mimic the weather and the environment of Mars. And in fact, he found some. That's kind of neat. He created this field that, for a while at least, was called astrobotany. That's evolved modern times into more astrobiology, and astrobotany could be part of that. But he found that, indeed, on Earth, some plants aren't green. Another person whose picture I could not find, William Weber Koblenz, was a physicist with the National Bureau of Standards working in Washington, D.C. in the 1920s, a very good radio scientist in the early days of radio. He decided he would use infrared filters to measure the temperature of Mars. And he measured at that time what were the most accurate measurements of the temperature of Mars. His measurements were very, very wrong, but everyone thought they were right because they were so accurate, apparently. he found that the dark areas of Mars had different temperatures than the bright areas of Mars. Not true, but that's what he found. So the bright areas had a temperature of about the freezing point of water, 32 degrees Fahrenheit. The dark areas were about 30 degrees warmer. And again, let me emphasize, this was all wrong, but everyone thought it was right, so it influences everyone's thinking. He then claimed that on the Earth, the bright areas are the hot places, the deserts. On Mars, he said the reverse is true, apparently. The bright areas are the cold places. Now, again, the logic is inescapably wrong because the coldest places on the Earth are the polar caps. The polar caps are covered with ice. Ice is very reflective. If you could imagine seeing the Earth from space, why wouldn't you conclude that the brightest spots on Earth are cold and that Mars is just like the Earth in that respect? Even if the measurements are all wrong, why couldn't he get the logic right? But he couldn't. The observed high local temperatures of Mars in the dark regions can be explained best by the presence of vegetation. Why? Vegetation which grows in the form of tussocks or thick tufts, such as pampas grasses, and the mosses and lichens that grow in the dry tundras of Siberia. So in those cold areas on Mars, the cold areas are dark areas which are warmer than the bright areas, but that's where you'd get the cold plants that grow in Siberia. Okay. Apparently, I just don't understand the logic. I can't take you there. But this is the introduction of some important words to the conversation, the 20th century conversation about Mars. This is where mosses and lichens could grow. And much of the rest of the century is going to be searching for mosses and lichens. Henry Norris Russell was the dean of American astronomy for the first third of the 20th century. He is the proverbial 600, 800, however much weight you want to give to your gorilla. He dominates everything. He invented a diagram that's known as the Hertzsprung-Russell Diagram, which is the Bible for astronomers. Everything you do in astronomy, you refer back to the Hertzsprung-Russell Diagram. He did that in the first decade of the 20th century. The most important prize in American astronomy, probably in world astronomy, is known as the Henry Norris Russell Prize. He's a big deal. He wrote, Mars has all the necessary conditions for life as we know it. In addition, the large green areas on Mars that change color with the Martian seasonal cycle makes it probable that vegetable life exists on Mars. So Henry Norris Russell, who everybody listens to because he has such authority in astronomy, says that Mars probably has vegetation because it has green areas that change color with the seasonal cycle. Where did the green colors come from? Mars is red, but suddenly everyone's looking for green colors when no one can find green in the searches for chlorophyll, which should look green. But if Henry Norris Russell says the green colors are evidence of vegetation, it must be true. Robert Trumpler is the next player in my drama here. Someone did a nice sketch, I guess, of Trumpler. Trumpler was also a very important astronomer. In 1924, he confirmed Einstein's theory of relativity. Everyone knows, or many people know the story, that in 1919, Arthur Eddington confirmed the theory of relativity. If you look at Eddington's data, it's pretty poor. The real confirmation came by Trumpler during a solar eclipse in 1924. That's what truly cemented our understanding that it was right. Trumpler is important for us because he discovered something called interstellar dust. Interstellar dust exists in between the stars. If you put dust in the air in this room, it's hard to see through. It's like a cloudy day or a smoky room at a bar. Interstellar dust makes things look fainter, but it also does something called reddening. This plot you see is percentage transmission in the interstellar medium. It's how much light gets from one star through the galaxy to another part of the galaxy. And it's a plot versus wavelength, and I've identified for you here approximately where the colors are. The amount of light that gets through in the blue is very little, 10%. In the green, 20%. In the yellow, 40%. In the red, a bit more. If the light is uniform in all the colors, the interstellar dust removes the blue and the yellow and makes things look red, makes things look redder than they actually are. That was his big contribution. In terms of Mars, in 1927, he said he'd identified a close relationship between the network, which would be the canal system, so he liked the canals. And the extended dark areas of Mars, which are of a bluish-green tinge. Again, I don't get it. Where did the red color go? Now the green is a little bit bluish-green. This relationship suggests the hypothesis that both are made visible by vegetation and that the network lines represent lanes of greatest fertility. Trumpler, despite how important he was in astronomy, this is the blemish on his record. Why he had these ideas, which are just so incredibly wrong, I don't know. He was one of the last believers in Lowell's and Schiaparelli's canals, and that's what he's talking about now. In the 1930s, we finally get to meet someone who does things a little bit wiser. This guy, Peter Millman, who I'll show you on the next page. This article was about searching for vegetation on Mars. He's following through on what Tikhov had done 30 years before, looking for evidence of green stuff on Mars. He wrote in the beginning of this article a piece which I use as the epigram in my book. So much nonsense has been written about the planet that it is easy to forget that Mars is still an object of serious scientific investigation. So he decided he would actually do a serious scientific investigation, not just wave his hands at the supposed canals and the bluish-greenish color that isn't there. He said, compelling reasons have led many astronomers to the hypothesis that Mars has vegetation. Let's test it. How is he going to test it? He's going to look at the colors of reflected light, sort of like what Tikhov did. He's going to study specific areas, the Syrtis Major region and Mare Terrenium, which are both dark regions, which if they're dark and the dark is vegetation, presumably are covered with vegetation. And he's going to compare that with colors of bright areas, which are right next to the dark areas covered with vegetation. And he actually has some data, which is wonderful, first time. The vertical axis here says magnitude. That's what astronomers use for brightness. Negative numbers are brighter than positive numbers because astronomers have a screwed up system for brightness. So on the top plot, you have a line coming down like here, which is identified as Martian seas. The Martian seas, I should say the x-axis is color with purple, indigo on the left, then blue, then green, then yellow, then red. The Martian seas, as you look at the Martian seas, they're brightest in the purple, and they get less bright toward the blue, and less bright toward the green, and even less bright toward the yellow. That's the color signature of the Martian seas. The Martian deserts are pretty much the same color at all, same brightness at all wavelengths. The bottom half of this plot is what you get in the laboratory if you shine light on chlorophyll. Chlorophyll gets brighter as you go toward the blue, and when you get to the green and the yellow, it gets super bright, and then it fades away as you go to the red. What he was doing is he's comparing this signature of chlorophyll in reflecting and absorbing light versus the signature of the dark and the bright areas on Mars, and the answer is there is no similarity whatsoever. And he concludes, neither the Martian seas nor the deserts reflect light in a way that would be similar to the spectral reflectance of chlorophyll. By the way, if any of you have a subscription to the magazine Sky and Telescope, this article was published in the Sky, which was the predecessor of the magazine Sky and Telescope. Then he says, although the dark-colored seas appear greenish in color to the eye, and again, they don't, the fact that they were relatively green and strong in violet blue and blue-green light, but weak in yellow, orange, and red, negates the existence of chlorophyll as an agent in producing that color. And I've provided you a couple maple leaves, since he was Canadian, to prove to you that leaves are green all the time. Not so much. So you can have other colored things. And we know of some plants, a burning bush plant, for example, which is redder. Right? You can find plants that are not green. He said, these results do not give any definitive evidence about the existence or non-existence of vegetation on the Martian surface. Finally, someone says something that's sensible. Okay? He has proven that chlorophyll is not obviously there, but that doesn't say anything about vegetation on Mars. What they do seem to indicate is that the greenish color of the seas cannot be taken as a support for the vegetation hypothesis, since the green color does not seem to be like the green reflected from our terrestrial leaves. And let me come back again to this plot and say, where's the green color? The Martian seas are less bright in green than in any other color, and the deserts are the same brightness all the way across at all colors. There's no green here. So even he is captivated by the idea of greenness, even though he couldn't see green. Maybe they're like me. Maybe they're colorblind. Perhaps, after all, we are rather presumptuous to think that anything on Mars which might have some remote similarity to biologic life on Earth would develop under the same organic system as that found here. That was reasonably wise. At this point, the search for chlorophyll has effectively faded away. No one's going to find chlorophyll, so you need to use other approaches to find evidence for life. Gerard Kuiper is the astronomer who in the 1940s started astronomy to move back towards studying planets, studying things in our solar system. As I told you before, Percival Lowell had so poisoned the water in astronomy that from the 19-teens to the 1940s, virtually nobody pointed a telescope at a planet, unless they were searching for chlorophyll on Mars, I suppose. Gerard Kuiper changed that. He's famous for having discovered methane in the atmosphere of Titan. Titan's the big moon of Saturn, which has an atmosphere. He discovered Miranda, which is the fifth moon of Uranus. He discovered evidence for what is called the Kuiper Belt. The Kuiper Belt is where Pluto lives. The Kuiper Belt is big in the astronomy news now because since 1992 or so, we've found thousands and thousands of objects out where Pluto is and beyond. It's like the asteroid belt, but in the very outer part of the solar system, and we call it the Kuiper Belt. In 1948, he took a color photograph of Mars. Guess what color it was? It was red, yeah. Okay. One of the things Kuiper did is he invented for astronomers, or he started pushing astronomers toward infrared measurements. He had what the press called a new heat light measuring instrument, and he used that at McDonald Observatory in Texas to study the light of Mars. I want to introduce you to what he found. Okay? The humble lichen. I had to Google and figure out what in the world a lichen was, but they're ugly or pretty little things. They come in different colors. A lichen is actually two things living together. It's a symbiotic creature made of certain kinds of plant cells combined with either algae or bacteria, so it has some photosynthetic stuff in it. Anyway, it's not critical to you to memorize what in the world lichens are, but lichens are very primitive terrestrial life that are interesting. They live in extreme environments. That's what's important for us. Kuiper designed an experiment to try to look for lichens. He, again, was focused on what he thought were the green areas of Mars. He had filters to study Mars at 4 different wavelengths. 0.6 microns is reddish light. 0.8 microns is very red. 1 micron and 1.6 microns you can't see. They're in the infrared. And he used these filters to observe Mars, and what he wanted to do is compare the brightness of Mars in these different filters, very similar to what the previous folks were doing. He said the green plants should reflect very well in the green and also between 0.8 and 1 microns, the near infrared. They should be darker at 0.6 and 1.6 microns, brighter at 0.8 and 1 microns. There's no test, you don't have to memorize that. But essentially, he was looking for color contrasts. 4 filters, Mars will be brighter in some, darker in others, depending on whether you're looking at the green stuff or not looking at the green stuff. And the result was there was no difference. Mars was equally bright in all 4 filters. He then said, as everyone else had done, there can't be any chlorophyll on Mars. He then said this rules out Earth-like seed plants as the dominant kind of vegetation that exists on Mars. But since it doesn't rule out vegetation, there must be non-Earth-like non-seed plants, or Earth-like non-seed plants, which are not like trees or grass. Not surprising, in view of the extreme rigors of the Martian climate, in particular the cold nights, Seed plants and ferns are both vascular plants containing a great deal of water. Such plants would undoubtedly freeze in the Martian climate. So it can't be trees and ferns and such. The reflectance spectra of lichens are what he found. Lichens look the same. He said the spectrum of these lichens and that of the Martian regions are similar between 0.5 and 1.6 microns. And in some ways, this is an extension of the astrobotany that the Russian astronomers started. Look at Mars, study the reflected light from an actual plant, find out that they're the same. Lichens had the same colors in reflected light as Mars. He then told us that if all the atmospheric water on Mars were made available to the green area, now remember we talked about that 25 microns of precipitable water vapor in the atmosphere, that's 1971 forward knowing that's the answer. He actually thought that was the right answer back in 1947 or so. The height, that total amount of water would receive a layer 20 microns thick. He had the right answer. The height of the living parts of the vegetation could hardly be more than 10 times that amount. So if you're living in a puddle, you can be 10 times taller than the puddle. That's the logic. Don't know what the logic comes from, but that's the logic. The vegetation could hardly be more than 10 times this amount or 0.2 of a millimeter tall. Presumably, it's much less. This estimate is compatible with a lichen cover. These are his words, his italics. The colors of Mars, the amount of water vapor in the air, the temperature of Mars is compatible with the lichen cover. Lichens, he said, produce very little oxygen, and even the traces set free would gradually escape the planet. Therefore, you'd never detect the oxygen produced by the lichens, so don't do that test. And he'd already proven that Mars has very little oxygen in the atmosphere. Therefore, the fact that observers had not detected oxygen in the Martian atmosphere is consistent with lichen life on Mars. No contradiction with the spectroscopic tests would thus result. Okay. So the lack of oxygen on Mars is consistent with the presence of lichens. They might be lowly lichens, like those that grow on the dry rocks near McDonald Observatory. Lichens need no water in liquid form. Martian lichen-like plants might get enough water out of the vapor from the ice caps, which evaporate without melting. He's coming up with a good scenario to make this work. Yes, ma'am.
You've talked about history and how people had said this and then they got proved wrong, and then somebody else said this and then part of it was right, part of it was wrong. What are the odds that 500 years from now we're wrong?
I'd say the odds 500 years from now is that we'll be wrong about a tremendous number of things. The question is, wrong in what way? Are you wrong because you're not completely right, or are you wrong because you're out to lunch? So Isaac Newton's theory of gravity is wrong, but it's not wrong. It's just not as right as Albert Einstein's theory of gravity, relativity. So relativity was an improvement on the theory of gravity, as opposed to a proof that the previous idea was bunk. I think most of this is bunk. I don't think we're going to find that there's lichens growing on Mars. There could be things growing in caves in Mars, but none of these observations can see inside the caves. So I couldn't tell you what's under the ground. I think this stuff isn't going to bite us in the heel. All right. His observations of Mars got a lot of press. Life magazine. You remember Life magazine? Life magazine published the photographs of Mars and said the newest photographs and studies disclose that life on the planet is limited to simple vegetation. Actually, what they prove is that Mars looks red, but Life magazine was quoting Kuiper. The green patches are vegetation, not might be. The green patches are vegetation, but of the lowest order, lichens, which live by drawing moisture from the air. The lowly lichens represent life's last stand on the red planet. Kuiper thought this was incredibly important as a discovery, not because he discovered life on Mars, because everyone knew there was life on Mars. This was important because he'd proven that there was no advanced life on Mars. There were no little green men. There were no advanced engineers. There are no polar bears or trees. All there is life's last stand, the lichens. Yes?
Did nobody ever think about bacteria? I mean, why so...
Did no one ever think about bacteria? I think at the time no one would have known how to look for bacteria. if you want to conclude that the lichen measurements are wrong, but maybe there's bacteria, that would be a reasonable possibility. And yeah, the lichens are wrong, so maybe we're down to life's last stand is bacteria. But no one was looking for bacteria at the time, so no one was talking about bacteria. They didn't know how to look for it. It would be tough to look for it even now, unless you actually go to Mars. The magazine called Science Newsletter wrote about this work that he discovered no trees, no flowers, not even ferns. The only possible life forms would be mosses and lichens such as that cling to lofty, frigid peaks here on Earth. There is no chance of the higher life forms such as the most primitive animals, much less anything like a man or a Wellesian monster. I don't know if it's an Orson Welles monster or an H.G. Wells monster, but either way. Observations are consistent with the existence of mosses and lichens in the green areas of the planet. This new picture of Mars may be a forecast of things to come. Now, here's how astronomers make their work relevant. A forecast of things to come for the Earth itself. Mars is a worn-out planet with conditions that probably will prevail on Earth many millions of years hence, when most of our atmosphere has been lost and mankind has long since disappeared. Last little bit of press for him, Time magazine, 1948, an article titled, "Mars is Just Right for Plants." Last autumn, Kuiper found that the atmosphere contains a small amount of carbon dioxide which is necessary to plants, the basic living organisms. Without any carbon dioxide, plants' chlorophyll, which they couldn't find, lichens and algae cannot live, but too much would indicate that there are no plants on Mars to consume it. The climate of Mars resembles Earth at an elevation of 50,000 feet. This probably would support lichens, since these plants act like sponges and suck up water vapor present in the air. Rain is not necessary for their existence. This was the beginning and the end of the lichen story. By the late 1950s, Gerard Kuiper spent a lot of energy trying to convince people he'd never said any of this. Okay? And no one else has looked for or found lichens on Mars. His successor in this hunt, however, looked for algae instead of Mars. Bill Senton was also a very good astronomer. He took what Kuiper had done, pioneering infrared astronomy, and took the work further into the infrared, to longer wavelengths of light. He understood that the big problem for astronomers in detecting these infrared wavelengths is that everything in here is producing infrared light. I'm producing infrared light, the desk is, the chairs are, the ceiling is, the building is, the telescope would be, the detector with my camera in it at the telescope would be, the atmosphere is, the clouds are. And all of that infrared light from all of that other stuff just overwhelmingly swamps the infrared signal you're looking for from Mars. So how do you deal with that? He said, I'm going to make my detector incredibly cold so it doesn't produce any infrared light of its own. That's what he worked on doing. So he was able to build an instrument that used liquid nitrogen that cooled his detector down to a temperature of about 96 degrees above absolute zero, 96 kelvins, minus 287 degrees Fahrenheit. It's cold. And that's as cold as anybody could get at the time, because liquid nitrogen was the prime thing to use to cool things off. And he then studied Mars at a wavelength of 3.4 microns. Again, that's way beyond what your eyes can see, but it's known as the near infrared. Why 3.4 microns? Why did he choose that region? He did that because in 1948, some chemists had shown that organic molecules absorb and emit light very effectively at about that wavelength. Organic molecules have a carbon and a hydrogen atom in them. Okay? They can be more complicated than just one carbon, one hydrogen. But the reason chemists have a whole class called organic chemistry is they're studying what happens when you put carbon atoms together with hydrogen atoms. Your body is made of organic chemicals, carbon-hydrogen bonded chemicals. And those organic molecules, because of the carbon bonded to the hydrogen, produce light or absorb light at that particular wavelength, in particular at 3.46 microns. So he decided if he studied Mars at 3.4 microns, and 3.3, and 3.2, and 3.5, and 3.6, Mars should be brighter on the ends and fainter at 3.4 microns because the organic molecules on Mars would be absorbing the light. He's no longer looking for chlorophyll. He's looking more generically for organic molecules. He published his first paper on this project in the Astrophysical Journal in 1957, spectroscopic evidence for vegetation on Mars. Not evidence against, but for vegetation on Mars. His work doesn't prove lichens exist, but does prove that organic molecules are present. We have rovers on Mars right now that are having trouble finding organic molecules. But he found it in 1957, he said. The dip at the significant wavelength is therefore additional evidence for vegetation. This evidence, together with the strong evidence given by the seasonal changes, makes it extremely likely that plant life exists on Mars. So here's what he found. More plots of how bright things are versus wavelength. The vertical axis says reflectance, the percent reflectance. If you're up at 14, it's reflecting 14% of the light. If you're down at 0, it's not reflecting much. Wavelength, this goes from 2.9 microns out to 3.8 microns, so again, your eyes can't see these colors. This is a maple leaf. The maple leaf reflects more light as you go to slightly longer wavelengths, and then around 3.4 microns, boom, it absorbs a lot more of the light, and then it gets brighter at longer wavelengths. That's the signature of that carbon-hydrogen bond in the maple leaf. The lily of the valley. I don't know what a lily of the valley is. Anyone know it? Yeah, okay. It's a plant, right? All right. Well, little white flower. All right. Here's your lily of the valley spectral thing. It's not as bright here, but you do have these, it brightens up when you get away from that 3.4 micron band. He then studied the things he needed to study. Here's one form of lichen, the top line. The bottom line's another form of lichen. And in between is moss. And as you see, as you go to the right to longer wavelengths, the lichen reflects more light. But when you get to about 3.4 microns, the bottom falls out. Right? It's not reflecting as much light because that organic molecule, apparently, is absorbing some of that light. Therefore, these organic things on Earth show this drop at 3.4 microns. If you can see that drop in the reflected light from Mars, you know there are organic molecules on Mars, and therefore you know there's vegetation on Mars. That's the logic. So here are his measurements of Mars. Each dot is one measurement at a different wavelength, and you can see very clearly as you follow those dots the big drop right here, right? Okay. If you see it, good. He got this spectrum early on using a fairly small telescope, the Harvard Observatory's 61-inch telescope. 61 inches is a couple feet across. The telescope is in Massachusetts. Weather sucks in Massachusetts for doing astronomy, but this was powerful enough as a first result to use as leverage to get time on a bigger, better telescope. That's what astronomers do generally. That's the game. Work with the telescope you have access to, get a good idea started, and then leverage that to get time on the biggest telescope on the planet. The biggest telescope on the planet was the Palomar Mountain 5-meter telescope, the 200-inch telescope. He got time on the 200-inch. This was a big deal. He used that to get more results, which were published here, further evidence of vegetation on Mars, but this time, instead of publishing in the Astrophysical Journal, this was published in Science magazine. Big publicity by putting it in Science magazine. The presence of large organic molecules is indicated by recent infrared spectroscopic tests. In this paper, he discovered what became known as the Senton bands. This top thing, you've seen the same sort of thing before. The vertical axis that's unlabeled is how bright the thing is. If the line goes up, it's getting brighter. Going to across this way is wavelength, but this is flipped versus most of the plots we've seen. So short wavelength is on the right, long wavelength is on the left, though that really doesn't matter for us looking at this. This top plot is what the sun looks like. You look at light from the sun in the region of 3 to 4 microns, and as you go from short wavelength on the right, water in the Earth's atmosphere absorbs most of the sunlight, and then it gets brighter, and then water absorbs some more, and then water absorbs some more, and then it gets fainter again. That's what the sun looks like. The middle one is a spectrum of a bright region of Mars. He happened to be looking at what he said is the Amazonas region, which is a desert region on Mars. If this is a map of Mars, this is your polar axis going from 5 o'clock to 11 o'clock. That circle indicates where he was pointing the telescope. And in that region of Mars, the spectrum looks like this. These dips here right in the middle are due to methane and water in the Earth's atmosphere, and Mars is reflecting sunlight, so it looks very similar to sunlight. Is there a little bit more structure in here, or is that just noise? He said there's nothing more there. This bottom spectrum is a spectrum of Mars looking at a dark region. In particular, in this map of Mars, you can see these two lines going across the map. He pointed his telescope at the region in between the two lines. That little triangle-shaped thing is Syrtis Major, which we've seen on lots of maps before. This looks very similar to the top plot, the reflected sunlight. That's what it should look like. Mars is reflecting sunlight. However, he said there's a difference. In this little region here, that little drop there at 3.43 microns, that one at 3.56 microns, that one at 3.67 microns, those are due to something happening on Mars. Something on the surface of Mars is absorbing a little bit of the sunlight that's incident on it. What could that be? He then did some more measurements in the laboratory of specific things. The top one is, dashed line is Physica, which is a kind of lichen. The bottom one is Cladophora, which is an algae. And he said both of them show this drop at about 3.4 microns. But Cladophora not only shows this drop, it's got the one drop and a second drop and a third drop. Cladophora looks just like Mars. So the lichens go away and the algae appears. Now we're focused on finding algae on Mars.
Did he have no people in his field that commented on this and took him to task for what he was
Well,
saying?
initially he gained some significant support, and then the house of cards fell down.
That's what I was wondering.
But in the meantime, I mean, this was big. From 1958 to 1965, this was huge stuff. Life had been discovered on Mars, and it's not lichens, it's algae. The bands near 3.5 microns, he said, are most probably produced by organic molecules, and these are produced in localized regions in relatively short spans of time. This is because the dark regions lighten up, and then they get dark again, and apparently when they get dark, that's when the vegetation is rapidly growing, and then it disappears again. Senton concluded that the similarity of the Martian spectrum to that of Cladophora demonstrated that what he observed on Mars was produced by carbohydrate molecules present in the plant. Even if he's right, all he knows is there's a carbon atom bonded to a hydrogen atom. That's all he knows. But he's taken that a bit further. It shows that it's produced by carbohydrates. The evidence points not only to organic molecules, but to carbohydrates as well. He then claimed that this was proof that the beings on Mars had to have large food storage capacities, because that's what carbohydrates are all about, so you can run the marathon. Some of the best support he got for these ideas came from this guy, Norman Colthup, who worked for Stanford Research Laboratories in Connecticut, not Stanford University, but a chemical research lab. He also published his results in Science magazine, which was very, very happy to be the publisher of all this incredibly good science. He said that the band seen by Senton at 3.43 microns was almost certainly due to a carbon-hydrogen bond that is in carbohydrates and protein organic matter in plants which resembled terrestrial plants. He then focused on two of those three little dips, the ones at 3.56 and 3.67 microns, and he said they are produced by specific kinds of molecules known as organic aldehydes, but not formaldehyde. Because organic aldehydes are among the few materials with a strong band near both of those wavelengths, as well as the band at 3.43 microns. Aldehydes, I had to learn some chemistry, and aldehyde is a chemical compound which has carbon, hydrogen, and oxygen, not just carbon and oxygen. So an organic molecule doesn't necessarily have to have the oxygen, but this has this group, carbon, hydrogen, oxygen bonded together. That's an aldehyde. He then went a bit further. He said there's a particular molecule acetaldehyde, I may not be saying that right, which is a very effective absorber at the wavelengths very close to 358 and 368 microns, which make it a great match to the spectral signature of Mars. So here was his plot. Science Magazine, 1961. The top line is what Mars looks like. This is Senton's data enlarged. We're going on the right from 3.4 out to 3.8 microns, and you have the 1 to the 3rd absorption band due to something. Number 2 is flower, not a tulip, right? But the flower in your kitchen. And that flower, for some reason, you only measure at the short wavelengths, but it has this first dip. And the bottom plot is his measurements of the reflectance spectrum of acetaldehyde, okay, which has these 2 dips that apparently Mars has. And therefore, not only do we know we're looking at algae, we know we're looking at a particular molecule in the algae called acetaldehyde. If I may be permitted to speculate a bit, you're going to see a lot of that speculation next week. If I may be permitted to speculate a bit, acetaldehyde may be an end product of certain anaerobic metabolic processes. No oxygen involved in breathing. This process is fermentation, in which carbohydrates are converted to acetaldehyde and finally to alcohol. This process yields much less energy for the organism than conventional oxidation, but certain organisms on Earth use fermentation as their source of energy when oxygen is not available, and perhaps this happens on Mars. That was the peak for the Senton bands. Now it's going to start going downhill. Okay. A handful of chemists at UC Berkeley showed that these little dips that he was seeing, they were chemists, so they use what's called wave number instead of wavelength. But those are the 3, those numbers represent those 3 dips that we've been talking about. Those dips, they said, might be due to deuterium oxide and heavy water. D2O is the same as H2O. Deuterium is a hydrogen atom with an extra neutron in the nucleus, so it's heavy water. You can have H2O, HDO, or D2O, they're all water. Right? And we talked about this a little bit last time in reference to gases escaping from Mars. They said that those little dips could be due to deuterated water, water that has deuterium in it. This is their plot. You should be getting used to seeing plots like this now, but they've flipped the wavelengths, so short wavelength on the left, long on the right. The bottom piece of this is the Senton spectrum, and you have 1, 2, 3 dips. Those are the supposed Senton bands on Mars. This is the acetaldehyde spectrum with some of those sort of dips. And the middle spectrum is a spectrum of water that has deuterium as part of the water molecules. And you see some of those same dips. And they suggested that maybe what Senton was seeing is not an aldehyde molecule, but is actually heavy water in the atmosphere of Mars. It was an interesting idea. This, to me, is one of the most interesting articles I've ever seen published. Okay? The authors are Donald Rhee, Brian O'Leary, I believe, and Bill Senton. Okay? The origin of these 2 wavelength minima, these absorption bands in the infrared spectra, this is again published in Science. In this article, they say that Senton got it wrong. The last sentence there in this abstract says, an important corollary is that there is no evidence for attributing these spectral features to Mars. What they did is they showed that those absorption bands due to deuterated water are not in the Mars atmosphere, they're in the Earth's atmosphere. And what Senton had discovered was heavy water in the Earth's atmosphere. So this top plot we've seen before. This is Senton's plot where he's got these little dips. These bottom plots are measurements they made on Earth. This says this was made in Denver in 1954, and the one on the right made in Denver in 1955. And the one on the right, there is less water vapor in the Earth's atmosphere. The one on the left, there's more water vapor. And when there's more water vapor, these dips get deeper. This is evidence that these dips at 3.57, 3.67, mislabeled right there, 3.67 microns, are due to water in the Earth's atmosphere. And what Senton had discovered was water in the Earth's atmosphere. The reason I think this is such an impressive paper is that Senton himself was one of the authors of the papers that showed that the Senton bands were completely wrong. You don't see that very often. That takes a tremendous amount of professional courage, I think, to go out there and say, I screwed up. Okay? And my screw-up has been some of the biggest news in astronomy for the last 10 years. They even have a name, the Senton bands. So now the Senton bands go down in astronomy history as a big, big mistake. So again, he had a lot of guts to do that. But now the Senton bands are gone. This story ends finally in a paper published by Carl Sagan and James Pollock. Carl Sagan is a name you know. James Pollock was also a very distinguished planetary astronomer. These two pictures, left and right, simply show you the darkening. On the right, you have a bright region in the north. On the left, it's a little bit darker. This is what's always referred to as the wave of darkening that comes about. It starts at the pole and it moves down. This is because there are giant dust storms on Mars that actually start at the poles and move away from the poles. They say here, the wave of darkening in the Martian springtime, which some say may have a biological explanation, can be explained in terms of wind-blown dust. And for those of you looking carefully in the top right, you'll see where this was published. Nature magazine, not Science magazine. Okay? Science magazine for more than a decade had been the place where everyone published stuff to show that the Senton bands proved there was life on Mars. And I think Nature was thrilled to be able to publish a paper saying, really bad decade, guys. All right. What Sagan and Pollock did is they used this radio antenna. You can call it a telescope, and it can be used as a telescope. But this is part of NASA's Deep Space Network. This is the Goldstone antenna in the Mojave Desert in California. It's 70 meters across, almost the size of the football field nearby. It's a big, big thing. It's mostly used to receive the signals sent back to us by spacecraft traveling through the solar system. So all our data from Mars, from Pluto, from Saturn, from Neptune, that data is fed into the Deep Space Network, and you need a big antenna to collect that signal because it's a very, very faint signal coming from these spacecraft. What they did is they used this antenna to actually broadcast signals, to send radio waves to Mars, bounce the radio waves off of Mars, and measure what comes back. And what they could measure was the topography of Mars. They could measure which areas were high, which areas were low, which areas had steep slopes, which areas had shallow slopes. And they concluded that the dark areas of Mars are at higher elevation than the bright areas. They concluded that the dark regions that exhibit long-term changes in color have smaller slopes and smaller elevations than the dark regions that don't change color. What they were effectively proving is sand is blown around Mars, and it's more easily blown off the shallow-sloped regions at low elevation because the sand is coming from lower elevation deserts, which can blow uphill, but it can't go 5,000 feet uphill. They then hypothesized that the long-term changes are due to the movement of sand and dust from the bright areas onto and off from adjacent dark areas of shallow slopes. So certain areas of Mars get bright when the sand is blown onto them. They're very reflective, and they reflect the light. And when the sand is then blown off of them, they darken again. The so-called regenerative properties of the dark areas, that is, the ability of the dark areas to darken after lightning, are due to winds scouring small deposited particles off the sloping highlands. So if we can say this again, the Martian winds blow dust around on Mars, dust and sand. The sand grains are very reflective particles. When the sand grains are deposited on a slope, the slope brightens. When the sand grains are blown off the slope darkens. Darkening has been misunderstood as springtime. It's not springtime. It's windstorm time. All right, so I'll leave you with the guy who solved this problem. And I'll take questions if you got them. All right. What we have now, dismissed the lichens, dismissed the algae, dismissed the moss. It's just sand. That's what's on the surface of Mars. Okay. The story doesn't end, though. We'll keep looking for life the next couple weeks. All right. Yes?
You said that Mars used to be a lot warmer.
Why did Mars used to be a lot warmer? In the very distant past, we're talking probably 2 billion years ago or more, okay, Mars was warmer because almost certainly its atmosphere was thicker. Why was its atmosphere thicker? Probably because it hadn't yet lost most of its atmosphere. With the thicker atmosphere, with more water in the atmosphere and carbon dioxide in the atmosphere, Mars had a very effective greenhouse atmosphere which warmed it up. But as bit by bit, atoms and molecules in the Martian atmosphere escaped to space, the atmosphere got thinner. As it gets thinner, it's easier for particles from the atmosphere to escape from space. It's easier for ultraviolet light from space to destroy the molecules, which makes it easier for them to escape to space. As the atmosphere gets thinner, the greenhouse becomes less effective. As the greenhouse becomes less effective, the Martian atmosphere cools down. When it cools down, the water starts freezing onto the surface. Instead of being in the atmosphere, now the atmosphere gets even thinner, and that makes it even tough. So it becomes a runaway refrigerator, if you will, when you start losing the atmosphere. Shouldn't it happen to Earth too? At the moment, no. A couple reasons. One, the Earth's gravity is stronger, so it's harder for things to escape from the Earth. Second, the Earth has life on it, lots of life. Life has produced oxygen in the atmosphere. The oxygen in the atmosphere has produced ozone in the upper atmosphere, and the ozone blocks out most of the ultraviolet light from the sun. The ultraviolet light from the sun is responsible for busting up the molecules. Ultraviolet light takes a water molecule and busts it into hydrogen atoms and oxygen atoms. The hydrogen is very light. It can bubble to the top of the atmosphere and escape, leaving behind the oxygen to rust the rocks, which is why Mars looks red. On Earth, the ozone stops the ultraviolet light so the water molecules don't get busted up. Even if that weren't happening, we have a magnetic field. The magnetic field blocks the solar wind. The solar wind are these particles coming out from the sun at 400 kilometers per second, which sandblast the top of a planet's atmosphere unless the atmosphere is protected from that. And the way you protect the atmosphere from the sandblasting of the solar wind is you have a magnetic field. The magnetic field holds off the solar wind. So our atmosphere is not sandblasted by the sun. Our atmosphere is protected from ultraviolet light because we have an ozone layer, because we have life that formed a long time ago. And the Earth's gravity makes it harder for stuff to escape. All those things contribute to the Earth's atmosphere being more robust, if you will. The Earth's atmosphere would be harder to hold on to if life had not developed 3.5 billion years ago on Earth and we never got that ozone layer. They work together. Okay? But as it is constructed now, there's no danger of the Earth losing its atmosphere. Yes, ma'am?
So where did Mars' atmosphere come from in the first place?
Where did Mars' atmosphere come from in the first place? When the planets formed, the sun and the planets formed from this giant cloud that gravity pulled together, and you got the big thing at the center of the sun, you got a disk around it, and in that disk of gas and dust, the planets formed. The planets formed from little pieces of things crashing together and sticking and making bigger and bigger and bigger things until you got planets. The Earth got its water and its oxygen and its carbon dioxide and its carbon monoxide and its methane and its ammonia, what astronomers refer to as ices, things that would be gases at hot temperatures, but at cold temperatures they'd freeze out as ices. We got those because the stuff that collided together to form the Earth had that stuff in it, right? Mars got that component of water and carbon dioxide and nitrogen and argon because the stuff that formed Mars had that stuff in it. Mercury, which is very close to the sun, formed from different stuff because if you're that close to the sun, the rocks, the pebbles that were crashing together had temperatures of 500 degrees instead of 300 degrees. And at those temperatures, the water would have been in vapor, not in the solid things. So Mercury probably formed without much or any water. And any water on the surface of Mars probably came from comets that have crashed into it. But for the Earth, most of the water came from the building blocks of the Earth that all crashed together to accrete, in the words of astronomers, to make the Earth. And then as the Earth warmed up, the water bubbled up to the top, to the surface. And then we held on to it.
Did I hear you say that the red on Mars was rust formed by the oxygen that was there?
Yes. The red on Mars is largely there, the same reason we have red beds on the Earth, red rock canyons on the Earth. The oxygen in the atmosphere rusted the rocks to produce the red color. The oxygen that produced the rusting almost certainly came from water, in which the water had been broken up into hydrogen and oxygen, and when the oxygen rusts the rocks, it stays on the planet, and the hydrogen disappears. Yes, sir? Yep.
Do we know why Mars doesn't have a magnetic pole?
Do we know why Mars doesn't have a magnetic field? Most likely because Mars is simply a smaller planet. It doesn't have as much mass as the Earth. It has 1/10 as much mass as the Earth does. That having less mass means less gravity. That means the internal structure of Mars is different, and it's the internal structure of the Earth that generates the magnetic field of the Earth. Even Venus, which is 85% the mass of the Earth, is not quite massive enough to generate a magnetic field. The Earth is just barely big enough to do that. So its mass, its gravity. What about the larger planets? All of the larger planets have magnetic fields. Jupiter, Saturn, Uranus, and Neptune all have magnetic fields. The Sun has a magnetic field. Big gaseous planets may generate their magnetic fields through a slightly different process. The magnetic field on the Earth is generated in the core. The magnetic field in the Sun is generated in the outer atmosphere. And on a planet like Jupiter, it may be a combination of those two things. But nevertheless, the giant planets have magnetic fields.
It sounds like to me, we just got really lucky.
We got really lucky on the Earth? Maybe. Maybe. You could conclude, I think, I'll say not unreasonably, that there's only one planet in our solar system that's capable of sustaining life over a billions of years time scale. Mars might have been capable of sustaining life early on, and if life has survived on Mars, because, again, if it got started on Mars, there are habitats, locations on Mars, such as deep in caves, where life might still exist, but Mars became a place where the surface of Mars became hostile to life. Venus probably was hospitable to life for 2 billion years. Then Venus got too hot, and Venus is not hospitable to life. Mercury never was. The giant planets, Jupiter, Saturn, Uranus, Neptune, never were. There are certain moons in the outer solar system we've talked about before that might be, but not on the surface. So yeah, the Earth might be the lucky place.
Using the probability that in the solar system we had 2 planets possibly that held life out of time, and thinking of all the other solar systems, all the other stars, the solar system, the probabilities of similar planets to Earth has to be higher, isn't it?
Given that 2 planets out of our 9, I like you used 9. Okay. 2 planets in our solar system, at least for a long period of time, were compatible with having life, with hosting life. Given how many stars exist in the Milky Way galaxy, given how many galaxies exist, statistically, it's easy to make the argument that there will be lots of other Earth-like planets out there. That doesn't mean they have life. That depends on a lot of other things. But there certainly must be lots of Earth-like planets. The other news in astronomy this morning is that the Kepler satellite is dead, speaking of other planets. The Kepler satellite was NASA's satellite, which was in the business of finding planets around other stars. It found more than 2,500 planets around other stars. That changed our conversation from saying, we think there are probably lots of planets out there, into, we know there are lots of planets out there. It's run out of fuel, so the Kepler satellite can't do any more work. It did great work for 9 years and made incredible discoveries. And there's a new satellite that was launched, I think in May, called the TESS satellite, which uses the same techniques as Kepler, looking for a planet that passes in front of the star, and that slightly darkens the amount of light you get from the star, and that becomes the signature of the planet you're seeing. So TESS is looking for planets in the same way Kepler was. So question here.
Yeah, you said we send radio waves to Mars and get the information back. How far can we send radio waves within our solar system?
We can. We are sending, how far can we send radio waves? We are now sending radio waves to the end of the universe. There's no limitation on that radio wave. So I Love Lucy is being broadcast to the end of the universe. It will It will take billions and billions of years to get there because the radio waves travel at the speed of light. In terms of our ability to use the radio signals we send to do anything constructive, if we're trying to talk to the New Horizons spacecraft, which is headed to a little object just on the other side of Pluto, it takes about 5 hours for the message to get to the spacecraft. It receives it. It sends a message back saying, here's what I'm going to do next. So we can use those radio waves to communicate in a two-way conversation with our spacecraft throughout the solar system. What these folks were doing, what Sagan and Pollock were doing, was bouncing the radar waves, the radio waves, off of the planet. And we've done that with Mars, we've done that with the Moon, we've done that with Mercury, we've done that with Venus. I don't think we've done it with objects further away from us than that. For a radio wave as opposed to in a rocket, the light travel time to Mars is a few minutes. I'm not sure exactly, but I think it's about 4 minutes, 3 to 4 minutes. So it's not instantaneous, but it's fairly quick. We've used radar to measure the structure of certain asteroids, but not asteroids as far away as the asteroid belt. These are asteroids called near-Earth asteroids, which are passing fairly close to the Earth, not as close as the Moon necessarily, but closer than Venus, closer than Mars. So radar's been used to measure the size and shapes of certain asteroids. If you see an asteroid image that looks like a donut or a barbell or some weird shape, that's using this same technique. Red shirt.
You keep talking about it, and we all talk about this life. You know, we don't think there's life. But are we restricted in our concept of life?
Are we restricted in our concept of life when we have this conversation? Yes. In the same way that all these folks were looking for chlorophyll, they were looking for signatures of organic molecules. These are experiments that make a lot of sense in looking for life that we would understand. How do we look for life that we couldn't understand? I don't know. There's a great book that I didn't write. There's a great book out there that's published last year, maybe 2 years ago, called The Big Picture by Sean Carroll. It's a thick book. You need a lot of time, but it's a fantastic book. He talks about this question, what is life? How would you possibly recognize life? He talks about a lot of other stuff in there, but it's the big picture about life and the universe and everything. Life is something which takes in energy and uses it to transform itself in some fashion. I think most people would agree with that. Now, we haven't yet talked does that mean it has to be chemical-based? Could it be a magnetic field that's life? He didn't talk about that. It's something that takes in energy and uses it to do something productive with it. What is it that life does that's productive? I don't know. But it reorganizes information. It reorganizes energy. That's what life is. Life, for us to look for life on other worlds, what we're looking for is an environment that is, as a physicist would say, out of equilibrium. It's an environment in which whatever we're seeing could not sustain itself in that form without intervention from something. In our atmosphere, and we'll be seeing this over the next 2 weeks because we're going to start talking about methane on Mars in 2 weeks. The methane in the Earth's atmosphere could not exist in the presence of oxygen in the Earth's atmosphere unless you keep pumping the methane into the Earth's atmosphere. So the methane in the Earth's atmosphere is a signature of life because the methane and the oxygen are out of equilibrium with each other. They could not sustain themselves together without some sort of outside influence. That would be a signature of life. It doesn't have to be methane and oxygen, but it would be a chemical environment that's out of equilibrium, that is unnatural. So we could look for that, but even with that, we don't really know what to look for. Okay? Take one more question, then I got to stop.
Well, I just found all those early eras so astounding. Then I remembered that when we wanted the Earth to be the center of the world, it's barely qualified scientists to make other eras. Do you think that humans had such a strong desire to find life elsewhere that was partly driving these otherwise good scientists to make such astounding eras?
I don't know if you heard all of that. We have a long history as humans doing science or even metaphysics of coming up with ideas which are wrong. The Earth is the center of the universe. Aristotle said this for 2,000 years. Everyone believed it. not obviously right. Okay. Have astronomers and scientists, more largely, created the idea that there should be life on Mars and then worked very hard to prove themselves right, rather than let the evidence actually drive their thinking? Yes, I think that's the case. That doesn't mean there's not life on Mars. But I think we have wanted there to be life on Mars. Therefore, we have allowed ourselves to interpret a tremendous amount of data, measurements, in support of there being life on Mars. And even when the measurements say otherwise, we just turn the corner and say, well, it's green instead of red, right? It's not chlorophyll, it's some other kind of life. I think we want there to be life on Mars. And in fact, there might be life on Mars, but at the moment, the evidence is pretty weak. Okay? And I think we've created a lot of it. But I think a lot of it was cultural. Over 150 years now, we have been pursuing life on Mars because we think Mars is an Earth-like planet, and therefore it should have life. I'm not sure why it should have life. It's allowed to be an Earth-like planet without having life. All right, thanks very much. We'll see you next week.